All right, in this video we're going to talk about the very bare bones basics of how a nuclear power plant works. Obviously you would not be able to make a nuclear power plant just off of what I tell you in this video, but it does give you the general idea of how it's set up. So the basic idea is that you have uranium-235 rods. I'm going to draw some pictures here, sorry. And each rod is below the critical mass. You're probably going to have hundreds of them, I'm just drawing 4. So these are U-235 rods, so they're cylindrical and they're usually pretty tall. And each of these is below the critical mass. Okay, oh, sorry. So the idea is each one of these rods by itself, if it starts undergoing fission, is going to release neutrons. And if it hits other uraniums, it'll keep going. But at some point, there won't be enough uranium for each of these to exist or to be self-sustaining. Okay, the reaction will die out. Now, that's the reason we have multiple rods, is the idea is each one is below the critical mass, so that if they're separated, it stops the reaction. But if you have them all together, you're well above the critical mass, and this thing will be self-sustaining and go on forever. Well, until you last millions of years, how about that? So, to make sure that we can control this, what we have in between them are what are called control rods. The control rods are basically able to go up and down. My picture is terrible, bear with me. So, I'll just draw an arrow to one. These are control rods. And they're just anything that can absorb neutrons without, violent reactions. So, the idea is if you pushed all of these down all the way, these would be completely separated and each thing would be below critical mass and it would stop the reaction. In America, we typically use cadmium. It's pretty stable, has a high melting point, it's not going to burst into flames. If there's too much heat, it's pretty stable. Okay. Now, what happens is this produces a lot of heat. Now, that's the energy coming off is in the form of heat. We need some way to make that heat, turn a turbine and make electricity. So all of this is underwater. Crappy picture time, I guess. I don't know. Sorry. All of it is underwater. Okay. And there's pumps pushing water all the way through it. So there's water pushed in this way, water pushed in this way. And the idea is all of this is underwater, and the water is there to help regulate the temperature to keep this from getting too hot and melting the uranium rods, which is totally possible. Uranium can melt if you produce too much heat. So it helps control the temperature, but it also removes the heat so that it can be used to generate electricity. Okay, so this is just literally water. I think it's actually mostly deuterated water, which means basically instead of hydrogen, it's H2, so it has a heavier mass and it moves slower, it's more dense, whatever. Okay, but this is the basics of how a nuclear power plant works. The uranium rods produce electricity as long as they're exposed to each other. So if you wanted this to be self-sustaining, you would remove the control rods. You would lift them up. Not necessarily all the way, but you would lift them up enough that these are getting exposed to each other so that they are above critical mass. And the uranium rods that keep getting shot out will eventually, or the neutrons that keep getting shot out will hit the uranium rods and the reaction will be self-sustaining. Okay. The control rods are there to absorb neutrons in case we need to slow this process down. Obviously, if you just removed the control rods, this thing's going to keep producing heat, and it's probably going to overheat and melt everything and explode. You need the control rods to help stop that. Okay, and the idea is all this excess heat is being absorbed by the water, and the water is being pumped through. So you have this continuous loop of water being pumped through. Okay, so this is the core of a nuclear power plant. This is the lazy gist of it. I haven't even drawn how they shoot neutrons at this to get this going. We're just kind of assuming once it's in place, this is how it works. Okay. So let's talk bigger picture. What do nuclear power plants look like? All right. Terrible art skills here. Let's see what I can do. So what you have is, I'm going to draw it like this. This is the core. So it's got the uranium rods, got the control rods, got everything contained. And the idea is This is all self-contained. The water that is in here never leaves. And I can't guarantee it's going to form a perfect square, but I'm trying to make sure it all fits. And the idea is that this thing produces a lot of heat, and the water pumps through here, and it just literally pumps through in a loop. Okay? This is known as the primary loop, because it's where everything starts. Okay? Without this, none of the rest of it means anything. Now, what happens is this pipework goes through what's called the secondary loop. The secondary loop is literally mostly just a big tank of water. Okay. And this is full of liquid water, but as this comes through, heat is lost. I guess I drew it blue in a previous video. Draw it blue here. Heat gets transferred in, and this creates steam. Okay. And literally this functions just like a steam engine. The steam goes up to a turbine and spins something around and generates electricity. Okay, so the steam, I guess we'll draw it in blue, steam goes in there. And this is what generates electricity. So this water, which has been exposed to radioactive uranium and whatever degraded side products are formed, literally never leaves that loop. It does not come in contact with this secondary loop. Okay. Now, most of the job of the secondary loop is to turn the turbine, but its other job is to cool down the core so this thing doesn't overheat. So as it's absorbing heat, the water in here is cooling down so that it's safe to keep pumping through and keep cooling the core. Well, this is absorbing a lot of heat and producing steam, but we need it to cool down also. So this is, if you've ever seen The Simpsons, why they have those weird cooling towers. My drawing skills are terrible. Here, look, we'll make it look like The Simpsons. There you go, terrible. The idea is, as the steam goes through the turbine, to cool it down, what happens is it literally just pours through the inside of the building and then gets pumped back into here. Okay. So I guess I should label this. This is the secondary loop. Okay. Kind of wishing I had more colors. Oh well. Now, this is going to produce a lot of steam. So if you ever drive by a nuclear power plant and you see this thing and you see what looks like smoke pouring out the top, it's literally just steam from heated water. There's no smoke, and there's no radiation coming out of this thing. It's literally just steam. It's basically literally making clouds. Okay. Now, this tower needs to be cooled also. So this is one of the reasons that nuclear power plants tend to exist near rivers or lakes. My picture's getting terrible here. Let's do it like this. So this is some sort of river or lake. Both are fine, doesn't really matter. And what happens is water is pumped out of the river or the lake, and then it's pumped through the cooling tower to help cool everything. I guess I could label this cooling tower. And then it gets pumped back into the river. So water just gets pumped through here. It's used to cool the secondary loop, and then it gets pumped back into the river. It has also not come in contact with anything radioactive. This is known as the tertiary loop. Tertiary loop. Okay. Now, the idea is, in theory, this the primary loop and at least half of the secondary loop, we don't want this stuff getting to the surrounding environment. So all of this is put in a building. God, I wish I had more colors. I'm gonna do it in red, sorry guys. So, try not to cut off any words that I've written. This whole thing is kept in a containment building. Not contained, containment building. And the idea is, if for some reason there was a leak or if there was an explosion, this containment building should hold as much as it is. We want to increase the likelihood that this thing is going to withstand any sort of leak or explosion. So typically it's made of about 10 feet thick of concrete and steel. It's pretty durable. Okay. But the idea is if there was some sort of disaster and the core like exploded or leaked your radioactive waste, it would be self-contained so that it could be cleaned up later without getting into the environment. As far as the waste products from this process, the core will last for years and years and years and years, but at some point there will be radioactive waste that we'll need to dispose of. Most countries in the world that have nuclear power programs have developed recycling processes, because the problem is you need these to be pure uranium-235, and honestly, once they get down to like 80%, 20% of it's used up, they're not efficient enough to be functional in this. So you could take them out and refine them and make new. You basically just purify them, get rid of the whatever else is in there, and re-purify them, and then they could be recycled, basically. Okay. America refuses to do this, and I can't figure out why. I have never heard a good explanation as to why America refuses to recycle this. Honestly, America's game plan right now is we literally take them out of here, and we bury them in a mountain in Nevada. Now, I'll admit I've traveled to Nevada. There's a whole lot of nothing there, so sure, why not throw our nuclear waste there? But I don't think we need to generate this nuclear waste. In all honesty, we could just recycle this, and we would have, instead of every single one of these really heavy control rods being buried into the ground to be radioactive forever, millions of years, we could just re-purify it, and we never, ever do this. Most other countries do, and it works great. I don't know why America's freaked out. So there are some situations where it's a problem to remove these. So honestly, there are some nuclear power plants that have shut down. They literally just lock down the containment building and make sure that it's continually cooled and the control rods are completely down and the reaction is dead, and then they just lock it up and walk away. Because it's pretty secure, it's designed to contain everything. It's not the ideal answer, but that does happen. As far as any other waste that is produced, it does produce a lot of, the other real waste that it makes is steam, is hot water. Some of it comes out as steam, which is not a big deal. You get that when you have coal power plants or any other form of electricity that has a turbine involved, like if you're burning something, okay? The main problem is that honestly, this tertiary loop takes river or lake water, runs it in contact with the secondary loop, and it cools it down, but in doing so, it heats up this water and then you pump it back in. Pumping hot water into the river or lake tends to heat it up enough eventually. It doesn't happen immediately, but eventually it heats it up to the point where the wildlife in that area gets killed off. Rivers are better for this, honestly, because there's moving water. You get fresh, new water in, and it can sometimes balance it out. Honestly, though, most nuclear power plants exist on the side of lakes. Those lakes tend to end up being mostly dead. And it's not because there's nuclear waste being dumped in there. It's literally just hot water. These plants and animals, these fish and whatever, are designed to live at certain temperatures. If you start pumping hot water in there, they die. That's literally it. So, in the grand scheme of things, as far as the safety of nuclear power, America has an amazing track record. Honestly, the world has an amazing track record of this stuff not exploding, not causing problems, not getting into the environment. There are 3 exceptions. And in class, I'll probably talk about them. I probably won't make videos about them, but the first one was Chernobyl. The very first one was 3 Mile Island. What happened in 3 Mile Island was a little bit of this water in the primary loop leaked into the containment building, and the whole thing got shut down. It never left the containment building. Okay. The second one, Chernobyl. Chernobyl was entirely human error. They didn't use cadmium for the control rods. They used graphite. And there was they misread something, and they ended up pulling all of the control rods completely out and then realizing that there was too much energy, and then when they tried to put the control rods down, they broke the uranium rods, so they couldn't separate them, and there was enough heat to set the the graphite on fire because it's totally flammable, which heated up the water, which basically split it into oxygen and hydrogen, which are both flammable, and the whole thing exploded. Okay. The third incident is Fukushima, which happened in 2011. This was in Japan, and honestly, they had literally state-of-the-art nuclear power plants. They all basically are variations on this theme. And honestly, what happened was there was a giant tsunami. Okay, so things that, you know, they actually had planned for. They had seismic sensors that basically, if there was anything above like a 2 earthquake, the control rods all went, it's called scram. They went into scram mode where everything was shut down. Everything was shut down. And so in theory, all the control rod, or the uranium rod, should have been separated, and it should have been as good as it could be. The problem was that a literal like tsunami, a giant wave, came and ripped the containment buildings and the core and everything apart. The containment buildings, which, you know, should be able to stand almost anything, a tsunami ripped it in half and destroyed everything inside, which kind of stopped the power to allow the cooling, so everything overheated and it exploded. Okay, that's literally one of the worst ones. Those have been the only 3. Other than us dropping nuclear weapons, humanity's been pretty good at using nuclear power. We're actually really, really good at it. So I highly recommend it. If you have the chance to, like, you know, vote for power sources in your area, nuclear power is a very, very viable and safe option. All right, thanks.